Hello again and welcome to a new lecture on mechanics. In this one we will introduce the concepts of shear force and bending moment diagrams. Now, you see, by cutting the beam at a point and drawing the resulting free body diagrams, one can calculate the internal forces, the axial force, the shear force and bending moment at that specific point. Now, if we're interested to see what's happening at other points along the beam, we can repeat the procedure at the other points and again calculate the internal forces in the beam at those points. Now, we can do and repeat over and over again this procedure at many points along the beam, like a very large number of points. So then we will know the magnitude of these internal forces at all points along the beam, and we can plot the magnitude of the axial force, shear force and bending moment diagram along the beam. This will produce what is called the internal force diagrams, and it's a very simple graphical tool that helps us to see how these internal forces change along the beam. Now, what we need to ask ourselves when we follow this procedure is how many points do we need to cut the beam at in order to get a good indication of the variation of these internal forces along the beam. So how many points are enough and not too many? Because as you can see, this procedure can be very time consuming. And maybe we can find some relationships to reduce the number of these cuts that we have to do in order to save us a lot of time and simplify the process. So we will see this in the next few lectures. But firstly, let's see how we normally draw these internal force diagrams. And we will do this through a very simple example in which you will see how to basically determine what's happening in the beam and how to draw the diagrams. So the simple example consists of a simply supported beam with loaded by a force P at midspan. So the force P acts at point C, which is half L, half the span L away from point A, and again half L, half of the span away from point B. So in other words, again, force P or point C is right in the middle of the beam. So in order to see what is happening in the beam, of course we have to calculate the reaction forces in the beam. And at A we had a pin. If we sum the force horizontally, the axial force AX at A is 0. And then through symmetry, it's a symmetric beam with symmetric geometry and symmetric loading on the beam. The vertical reaction forces at each end will be half P. AY is half P, ABY is half P. Now, the next step would be to verify that these reactions are correct, because if they're not at this point, everything else that you do will be incorrect. Now, let's see what's happening inside the beam. So firstly, we will cut the beam just to the left of P, infinitesimally to the left of P, as you can see. Cut 1 here in the figure, and let's draw the resulting free body diagrams of the two members. I'm going to draw them staggered just so I can properly draw the internal forces at point C. So these are the external force, the reaction forces. Now I'm going to draw the external forces, and when I do so, I will guess their direction, but it's a good practice just to show them with their positive directions, because if your result is negative, that will be the actual sign of that internal force. I'm only showing the shear force and the bending moment. As you can see, there is obviously no axial force in this beam because the forces have no component along the beam and the horizontal reaction at A is 0. So if you look at the equilibrium of the left-hand side, for example, we will get that the shear force will be positive half P and the bending moment positive P times distance x divided by 2. So the shear force is constant, the moment has a linear variation. Now I'm doing the same thing, but cutting the beam just to the right of P, infinitesimally to the right. Again, drawing the free body diagrams. Now you can see that P has jumped to the left-hand side free body diagram because the cut is to the right of P. And our goal is to figure out what's happening in the beam to the right of P now. Before we wanted to see what happened in the beam to the left of P. So these are the two free body diagrams, again with the positive directions by sign convention of the internal forces. And now if we solve for V, V is negative P over 2, so there was a big jump from positive P over 2 to negative half P. And the moment is now P times L minus X divided by 2. So now all we have to do is plot the shear force and bending moment diagrams on two graphs. Let's start with the shear force. Like so. And the hatching indicates the ordinate, the shear force intensity along the beam. You can see there's a jump right at the location of the force from positive P over 2 to negative P over 2. And this is the shear force diagram. I'm also indicating V in a circle, that this is a shear force diagram. And I'm indicating that the parts above the line are positive, the ones below the lines are negative. For the bending moment diagram, we know the magnitude of the center and we know that the moment varies linearly. We also know that the ends of the beam are pinned and supported by a roller, so therefore are free to rotate, so the bending moment at that point is 0. And the value of the bending moment at midspan is PL over 4. And of course, again, we indicate that this is a bending moment diagram. And we also indicate the signs of this diagram. So, in conclusion, what we have learned from this example is that for a beam that is subjected to concentrated forces, number one, with regard to the shear force, its diagram is constant along the beam between the points of application of the forces. However, wherever there is a concentrated force, there's a jump, a discontinuity at that location, which is equal to the magnitude of the force and it's in the direction of it. So for example, at point A at the left-hand side of the beam, the shear force jumps from 0 up to half P. Then at point C, the shear force jumps by a total of P. So plus half P minus half P equals to a total of P. And then at the far right end of the beam, the shear force jumps up by half P again and ends up at 0 where it should end up. Now with regard to the bending moment, that is 0 at the ends of the beam because of the pin and roller support, which allow free rotation of the ends of the beam. And then the moment varies linearly along the beam between the points of application of the concentrated forces. So we can see here some guidelines already on how to draw these diagrams and their shape for a simple case of a beam which is acted upon by concentrated forces. So thank you very much for watching this lecture, and I will see you at the next one.